quantum extremal surfaces. There will be two interesting branches. The first is to look for a quantum extremal surface near the bifurcated horizon. I'm going to call this the early time branch. The bifurcated horizon continues to be so even after turning off coupling, continues to be a classical extremal surface, but it is not quantum anymore. The reason being is that the state on this slice after the coupling has been deformed because some of the Hawking radiation escapes the ADS2 space and enters the back. And therefore, performing a variation of, for example, the dilaton piece near the bifurcated horizon, one would obtain, it would go as L squared over G Newton, where L is the variation parameter, while the variation of S bulk will be linear in L multiplied by C. C is the central charge of the bulk BCFD. This implies that there's a quantum extremal surface at a distance that goes at C times G Newton away from the event horizon, or the bifurcation surface. This actually should be a minus CL, but it doesn't matter. So you do this and you find that there's a locus of quantum extremal surfaces near the bifurcated horizon. They look something like this. Each point corresponds to a different boundary point in this fashion. And you find that there's an accumulation point somewhere here. Okay, so that's the early time branch. There is another set of relevant quantum extremal surfaces, all of which are to the future of the shock, which I call the late time branch. And let's go through the extremization procedure a bit more carefully. So we first try to extremize along the outgoing direction, and given that this is a black hole spacetime with an event horizon, we can search for a surface near the apparent horizon. So that's the region where the outgoing derivative of phi is 0. Okay, but that's not enough to specify the surface. We also need to extremize along the ingoing direction. Now we have a bit of an issue. The ingoing derivative of phi near the apparent horizon is actually order 1 and negative. This is just a statement that the area of the transverse spheres in a black hole spacetime near the apparent horizon, at least in this case, are contracting in the ingoing direction. And therefore, this term here is going to be 1 over G Newton, and so must be compensated by a large gradient in the bulk von Neumann entropy. Now, we can actually achieve this, and schematically, this is not exactly what the equations are, but schematically this is what happens. The entropy in the bulk is roughly, goes as the central charge times the log of the length of the interval, and therefore, if we work in the null limit, taking into account that the derivative, or the gradient is c over the length, which is the derivative of this guy, this means that we can balance this equation by taking the length of the interval to be c times G Newton. Now you might worry and say, but isn't this interval really, really small? No, it's fine. And the reason being is that we can work in the limit where the bulk central charge is large, but not too large, so that the length of this interval is parametrically larger than the Planck length. Okay, so we have two sets of quantum extremal surfaces, these green guys and these purple surfaces near the apparent horizon, and I'm going to plot what they look like as a function of time. Before I do that, on this plot I have the Bekenstein-Hawking entropy of the right side of this spacetime. And where I've isolated the ground state entropy from the thermal entropy above extremality. When I write delta S, I will always mean the thermal entropy above extremality. And what happens is that it gets a spike because of this shock that falls in, and then it decays exponentially. That's just a feature of KT gravity. Okay, so let's look at the early time branch. So what does this look like? So the quantum extremal surface, as we said, is near the bifurcated horizon. This means that the dilaton term is going to stay essentially constant, and all of the time dependence is going to come from the bulk entropy piece. Where at late times, you find that this term simply increases and saturates at some value. But something interesting is happening at early times. So when you first turn on the coupling, what you find is that the entropy first goes down. This is simply because the Hawking radiation is escaping the system. That Hawking radiation was entangled with the left CFD, or left boundary. But then, after the scrambling time defined with respect to this energy that falls in, the entropy turns around. I should say that this scrambling time for near extremal black holes was found by Leichenauer a long time ago, and we seem to reproduce it here. But let me explain why this effect happens. So when you throw energy into a black hole, you in some sense rejuvenate it, and let me take a step back. If you have a black hole that is maximally entangled, and then you throw some pure matter into it, you rejuvenate the black hole, allowing it to get more entangled with its Hawking radiation. But in order for that to happen, you need to wait for scrambling time for the black hole to actually have access to these new spatial states. Okay, so that's the early time branch. Then there's the late time branch, which, as we said, the quantum extremal surfaces are near the apparent horizon. This means that the dilaton value in this branch of the entropy will simply follow the Bekenstein-Hawking entropy all the way. So we have these two contributions, these two possible branches for the entropy, and the actual von Neumann entropy of R is the minimal one. So we need to apply the minimality constraint, and lo and behold, we have a page curve. The entropy of R goes up, and then it turns around and comes back down. Okay, so does this solve the information paradox? No, not yet, because we didn't analyze the path. So the question is, what does the entropy of the path do? So you can compute this using DFT techniques, and you find that the entropy simply goes up and saturates at this value. We don't really understand this factor of 2 yet, but it's 2 times the thermal entropy of the initial energy of the black hole plus the shock. And you can, so in order to deduce if there's information loss or not, you need to check if this entropy violates any entropic inequality. One such inequality is Iraqi, which places an upper bound on the entropy of the bath being less than the entropy of the sum of the entropys of the left and the right. Plotting SL plus SR here, that looks something like this. And so we see there's not a problem when the ground plane entropy S naught is large. But just because this is not a problem does not mean that there is not a problem in general. In particular, something that we can do in this case is that we can ramp up the energy of the shock, which was thrown in, and all our calculations actually just simply go through. And you find that the entropy of the bath increases monotonically and exceeds the entropy of the left plus the right. So this is information loss. So we failed to find a page curve for the bath. And this reproduces the standard Hawking result. This is actually a sanity check. The calculation that we did is identical to Hawking's calculation, so it's no wonder we got the same result. And so this doesn't resolve the information paradox. But now let me tell you how to resolve it. Consider the following crazy proposal. Let's say that the 1 plus lefty bulk bath CFTs living in this 1 plus 1 dimensional spacetime is holographic. So this 1 plus 1 dimensional spacetime or system is dual to a 2 plus 1 dimensional bulk coming out of the board. This slice here it corresponds to this slice of the spacetime, where the new holographic direction is pointing downwards. Let me see. Now, here on this spacetime we have a BCFT on a strip. On this spacetime we have a BCFT on the half line. It is a prescription of holography or boundary conformal field theory to extend the boundary of the conformal field theory into the bulk as some sort of end-of-the-world brane, or what we call an IR brane. Okay, so this is what you'll find. And at this stage we need to be careful about what we mean. The boundary holographic system is composed of these three systems, and the JT theory should be thought of as living in the bulk on what we call a JT brane. This JT brane lives on an ADS2 slice of the ADS3, which is in the holographic direction. Okay, so now let me tell you about the dynamics of this three-dimensional bulk as we couple B to R. So what happens is that the IR branes connect, and as you evolve forwards in time, the IR brane simply recedes into the bulk in this fashion. Okay, now let's compute the entropies. So, say we want to compute the entropy of the left. We can use the usual RT formula, or HRT, in the 2 plus 1 dimensional bulk. And it says that the entropy of L, for example, is simply given by the area of this RT surface. Or rather there are two contributions coming from that surface. One comes from the contribution at this anchoring point on the JT brane. Because the JT brane is dynamical, you actually pick up a Tillicon factor. And you also get just the length of this RT surface, which gives you S bulk. So the bulk entropy on this slice has been geometrized into the area of the RT surface in 3 dimensions. This is what usually happens. So this is at this time, this evolved to a time after the shock. Now the bath has non-zero entropy, and it now has an RT surface in the bulk. And that looks something like this. This is this orange line. The R system gets a new contribution to the RT surface, which is given by this green line. And it is this contribution to the RT to the entrance of R and D that is responsible for the first increase of study until the entropy. This light blue region of the JT brane. This light blue unfortunately, this doesn't feel like the octopus space-time, but as Stephen Checker said, now we have a nice single fillet of salmon. Okay, so the punchline is we managed to obtain a Page curve for both the evaporating black hole and for the radiation. And sometimes we also found, or we sometimes pinned down, quote-unquote, Hawking's mistake, which is that he didn't know about the minimality condition of the RT formula, but also he didn't know about the RT formula. Also, just before I go on to question and answer period, somebody should ask me about Q states. Thank you.
In my review talk, I promised everybody that the quantum extremal surface would lie behind the event horizon, and as seen in pretty much any one of your other slides, here it does not. So I was thinking throughout your talk, why does this happen? And I think it has to do with this shock where you couple the boundary to this other system, and it emits a pulse of negative energy. I'm pretty sure that pulse of negative energy will cause the generalized second law to no longer be true on the causal horizon that's the uppermost, that thing there.
That's not the horizon. The horizon is here. That's just the extension of the path horizon from the left.
Well, so the one on the left is the boundary of what an observer can see, who stays in the original space-time, maybe? No, I'm not saying you necessarily have a contradiction here. That's certainly, the fact that that dashed line that does not satisfy the generalized second law is why you violated that theorem. But do you have a comment on what you think the moral of that is?
I'm not sure I understood that. Let me correct something. I think you said that this yellow line has negative energy. Did you say that?
I thought you said that.
No, it has positive energy.
Yes, positive energy.
Yes. But there's negative energy that falls in. Because the fact that you have the vacuum in the back, that translates into both to having negative energy falling in. And the interpretation of that is simply that the